Back at it again. So the vector, initialize the numpy variables, then forward pass, define the symbolic, y pred is to make the prediction. We'll do this kind of loss function. And then this is the replacement of variables. But we're not replacing W2 because we're doing symbolic derivative of the loss with respect to W2. I will eventually crack this. Comparison. Okay, so if I run this, what's going on actually? Loss substituted. I just wanna I guess what I'm trying to get at is, okay, so that's the matrix, or what? So we have a loss function, and this loss function is basically a function of all this kind of stuff, right? Includes the prediction. Okay. What is the next thing that it prints now? What is the next print statement? This one here. So what I'm trying to do is I'm trying to I've substituted everything in the loss, so now it's everything as a function of W2. Because in exactly, because I have my loss function, and what I want to do is I want to just basically do everything as I want to. Although that's not. I think I kind of went one step backwards, right? Because that's ultimately not what you want, right? I mean, what I was trying to originally do here is trying to see if I could kind of derive that like the actual. Yeah, but I mean, it is actually with respect to W2, it is what it is. Well, it's not, because I'm actually replacing things, right? I'm substituting actually I'm substituting W1 I'm I'm actually replacing these values in here. But I mean, okay, in a way, not that it's bad to do these, but it's I mean, they're supposed to be constant. Like, if you're doing a derivative with respect to W2, everything else is supposed to be just a constant term, or you should treat it as a constant term, should you? I think so. I guess that's what makes it difficult, or what made it difficult here. Because if I just say these, then it's a much bigger monster, right? That it has all the other stuff in it. It has all the other terms, yeah. Then there's this big thing in here. But then, why wouldn't these work? Div. So how does div work? How does div work? They improved a lot, by the way, the AI stuff here, because now you can have multiple chats and stuff like this. So can you explain me how the function from SymPy is parameterized and how to use it? The function you differentiate and the symbols variables with respect to which you want to differentiate. Okay, so you actually have to give it a symbol. Yeah, okay, that makes sense, right? Because you diff f and x is going to be the symbol. And here, let's say, let's not substitute. How do you comment the whole line in Python? How to comment a block in Python? How do you? I forgot. Wasn't that? Ah, yeah, sure. Okay. Thank you. So we've got the loss. So okay, so what if we do this loss with respect to W2, but is W2 is the symbol here, right? Print derivative. Okay, so it's actually blah. That's a huge. This is huge. This is huge, huge. Because it's got all the terms, right? W1s, W2s. Got absolutely all the terms, but like, I guess the point is, who cares, right? This should just be okay. If I know, the point is that if I now replace the point being, that's the derivative with respect to W2. And the point being that if I now replace I think I've done that already. So we do the derivative, and now test this expression equals, we're going to apply the chain rule. Okay, so we got the issue. Okay. So we got this fine. So we have this thing, and then so this is the initial values, and now we're doing numerical. So now we're doing the numerical calculations. And we do these, and then what we want to compare. So now is exactly, and now we should be able, we should just be W2, right? Now should be replacing everything. So we're substituting everything, and then basically do derivative. So this would be, so I will actually name these symbolic. It's fine, I don't really need to print that, to be honest. We don't really need to print these. But then we can actually so we do these. Okay, we'll make the initialization of these values here up front, doesn't matter. Then we do the substitution in here, so then we just basically say print this one, right? So substitute the dictionary. So we're assuming the substitution is correct, and then with the numerical calculations, they compare this. Then we let's see. First of all, we're gonna do the comparison later anyway. So stop. Can I run? I guess what I'm trying to say is, you know, like if we've got tools like these, I wonder, one of the things that I want to check next then is I wonder how do then libraries like SymPy and stuff like that, not SymPy, how do libraries like TensorFlow and these guys, how do they do the derivation actually, right? Because this is obviously like the chain rule is obviously something that you do by hand, kind of, right? So you figure out how to do this, and then you kind of like do it by hand. But how do they do these? That would be maybe one thing to ask. Why is this taking so long though? The substitution maybe is taking long, because this definitely didn't take long. because that's still running, right? That's whatever it's running, yeah. AI. So how do ML libraries like TensorFlow implement derivation in a generic way? Do you have to give them the derivative yourself? I don't think so, right? Maybe they just do some sort of numerical derivation. Automatic differentiation, that's what I thought. Automatic differentiation, it can be, that can be, that's an interesting thing. So it allows, automatic differentiation allows for the calculation of gradients efficiently, which is essential. A specific form of automatic differentiation known as reverse mode automatic differentiation, which is particularly suitable for functions with a high dimensional input. Computation graph construction. It's called computations as a graph where nodes represent operations like addition, multiplication, and edges represent tensors. When you define a model or a mathematical operation in TensorFlow, it constructs a computational graph for a pass. Computational graph, reverse mode automatic differentiation, the gradients, reverse mode automatic differentiation. After the forward pass, it performs a backward pass, starting from the output back to the inputs. During this pass, it traverses the graph in reverse order and applies the chain rule of calculus to compute the gradient of the output. But they cannot apply the chain rule, because that's like, how do they do that? Gradient tape. Custom gradients for operations, particularly useful when the operation might not be the most efficient way. But how do they calculate? How do they apply that? How does TensorFlow apply the chain rule? Like they probably can't do this symbolically, right? Why is it taking so long? What have I done here? Like, it was just a breeze when I did this last time. Why does this take so long? It's just an operation. Cannot be. Oh, because it's a big operation. I guess because before, when I did it before, the substitution is so inefficient. Substitution is so inefficient? I guess so. So automatic differentiation, custom gradients. No, that's like, give me the same answer. You gave me the same answer. TensorFlow or PyTorch. How does PyTorch automate differentiation? On the fly, nodes represent tensors and edges represent the functions that produce output tensors. Going backwards and compute the gradients. This is done through the chain rule. This is or that, do they mean by these that because it's a computational graph, that's how essentially that's representing the chain rule? Requires gradient, but how? But how does the library do the derivative of sort of the unique nodes? How to say that? Of the isolated operations, or the of the operations in the computational graph. Additionally, your performance tensor is a node. Then you calculate something using tensors that require gradients. When you calculate something using tensors that require gradients, PyTorch builds such a graph under the hood to keep track of which operations are performed and how they are connected. Building the graph during the for a path, when you calculate the opposite, PyTorch builds the graph dynamically for operation. Okay, so how the results are computed backwards, so trigger backwards. Once you trigger backward, then once you reach an output and calculate, and once you reach an output and calculate a loss, you trigger backward propagation by calling backward on the loss tensor. This is where PyTorch starts computing the gradients. It looks at the computational graph it built during the forward pass. Starting from the node corresponding to the loss, PyTorch works back through the graph node by node. At each node, it looks at the operation performed and then applies the chain rule to compute the gradient of that operation. That's what I'm not. No. Like, I don't think that's how it works. Is PyTorch open source? Maybe github.com. So is PyTorch, is PyTorch open source? I think so. I think it's open source, right? Yeah. Installation. We might as well look at these. Actually, backward. I mean, I don't even know how the code base is structured, so what am I even looking at? I have no idea. Code owners, Torch. What is this even build on? On Python, I guess. Stupid. That was a stupid question. Did it finish at all? Okay, so it did actually finish. It gave me this matrix. Five minutes. Okay, so we'll give it 5 more minutes. Let me give it 5 more minutes. Okay, so let's run it for 5 minutes and let's just see again the two inputs. I'm sure they're different, but you know what I mean, right? So the for that better. I'd like to get it to work at least. It's just like at this point, it's just like me, wishing that I can just get this to work. Give me a second, guys. So. Okay. At this point, I just want this to work. You know what I mean? Just to kind of have that the two things at least match, just out of my own like comfort, that that's a way that you could do it, right? Because I like to kind of think of different ways you can do things, right? And obviously you can do like the, hey, let's just calculate by hand what is our thing. But obviously if people have implemented things like PyTorch, like they've automated the differentiation part. And I can't believe that like this is bullshit. This is definitely BS. I think like that's the AI just not knowing how to explain it. First works back through this graph and each node performing then applies the chain rule. No, you can't apply the chain rule. What does it even mean? At some point you have to do something. I guess I need to understand maybe the computational graph better. PyTorch. I guess, can I go to perplexity? And oh, actually it's a default. So PyTorch computational graph. Okay, so there's actually a few explanations in videos. Sorry, that's good actually. I could read a few things. So automatic differentiation. Okay, we could read that. I mean, okay, it involves the chain rule, but I guess my understanding is, that the point of having the graph is that represents the chain itself, right? That's kind of like the chain rule. But still, how do these... Wow, I think I would need to go back to like light mode for this page. Can I just, because that's like awful. Hologram. Okay, we can read through these things, and this probably is still computing. One more minute. One more minute. But essentially, can't get this boss. Yeah. Autograd, okay. Modern neural network architectures can have millions of parameters from a point of view. For a path to compute the value of the loss function, a backward path to compute the gradients of the learnable parameters. The forward path is pretty straightforward. The output of the layer is the output, input, and next, and so forth. So example, it's neural network consists of 5 neurons. Our neural network looks like the following. B equals W. That's a neural network. That's not the... Oh, that's the computational graph. B. Can I switch to light mode? Aha, there's a reading mode. I didn't know. Can I switch to light mode? Ah. In this case, how do I switch to light mode? Light mode. Yeah, but why doesn't it actually? Why doesn't it actually save that? Or this is a fucking shit here. Oh man. Anyway, competition graph. Okay, so you actually have multiplications, blah 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 blah. Okay, we'll read through these and how do they do these? I guess it's a way to think of the chain rule, yeah. And here, okay, so yeah, they're completely different, right? So there's nothing to do with like nothing. I'd love them to match though. I really would love them to match. That's what I'm not so sure. And maybe you know, the thing is, maybe I shouldn't. Maybe I should remove the softmax next time and see if they match without the softmax. I'd love them to match. I don't know why. If it had an easy way to compute this kind of stuff, you know. Yeah. Anyway, see you next time.